for coming. So I should maybe preface this that this is going to be a more high-level talk about some of the ideas and where these ideas come from. And then the last 15 minutes or 10 minutes are really about some of the very recent work we're doing. So I'm happy to talk about that.
I did ask you for a very high-level
talk.
So
that's what it is. Okay. All right. So why does it not work? This is not working.
did we check that it would?
Wait a second.
Go for it.
Oh. Okay. Oh, yeah. Okay. That works.
Exactly.
Program.
All right, okay. Well, obviously programs go wrong. Good example. So everyone who has written a program, I'm sure in this room knows programs go wrong, and not only do programs go wrong, actually compilers go wrong. Okay, so which are basically the programs we use to transform and compile other programs. And compiler bugs are in some sense particularly hard to find and fix. In particular, every programmer and every program is affected and potentially at risk. And if you think, well, that's a solved problem, okay, doesn't happen to me, okay, has never happened to me. Well, and there's a more recent study from 2016 where they looked at a decade of bugs in GCC and LLVM compilers, and they investigated 50,000 bugs, 30,000 bug fixes. So that's an astounding high number in systems that are used every day. So what is a compiler? Okay, so a compiler is a particular metaprogram. It takes in a source language and it translates it into a target language. And usually there's a whole tower of these languages. And more generally, you can think of metaprogramming as the art of writing programs, like a compiler, okay, that will produce another program and might also manipulate those other programs. And if we think about metaprogramming, then there are a couple of distinctions we should try to make. Okay, so the compiler often would be written in another language than the language you're trying to compile. Okay? So that is often what we call a heterogeneous metaprogramming approach. But you could also bootstrap your system, and then you're writing sort of a transformation within the system itself. And so then you would be writing programs that produce and manipulate other programs within the same language. So the idea of metaprogramming goes back a long time. So some of the primitives go back to Lisp and Scheme. But any of these systems, you see probably three different kinds of primitives. Okay, so the first one is something like quasi-quotation, which allows you to get access to the abstract syntax tree of an expression. So if you have the expression 3 plus 4, essentially think of it as the abstract syntax tree that has a node plus and 3 and 4. If you have the expression 3 plus 2 times 2, then it's kind of a deeper tree. And if you want to represent functions, like this morning we had the lambda calculus, then you also need to somehow represent this fact that you have a binder, okay, so that this x here is somehow binding this x. Which might not be captured here completely in this graph, okay, because we don't make a distinction between these two different nodes, but that would be a representation of this, this function. And unquote or splice is essentially allowing you to compose two syntax trees together. Okay, so if you assume that unbox square actually produces a syntax tree, 2 times 2, okay, it doesn't do yet the computation, produces that piece of syntax, then you can compose it into a larger syntax tree, so you get essentially this tree. That's the tree you're getting. And 3, okay, the third thing that is often present in these systems is evaluation of your syntax, okay, or of the code. So eventually you want to actually run and compute what is this piece of syntax you built. 3 plus 2 times 2, and if I did the calculation right, then it should compute 7. Okay? And it would usually reuse the runtime system of the language that you've already used to manipulate these syntactic objects. Okay, so who has used metaprogramming here? All right, cool. How? Like, what system did you use for metaprogramming? In the back?
Lean.
Lean. Okay.
Anacta.
Anacta, okay.
Template Haskell?
Template Haskell.
Prolog used to maintain.
Prolog, okay. Anyone else?
MetaCamel.
MetaCamel, okay. You're already advanced metaprogrammers. So, many people find metaprogramming, you find it in Scala, in Lisp, in C, C++. But of course, you also find it in proof assistants. And there are many good things about metaprogramming. It's pretty much supported in virtually every language out there. You've already heard template Haskell, MetaML, Lean and Coq is also Scheme, it's also supported. So it is really widely supported, pretty much anywhere. And there are good reasons why it is supported. So from a programming perspective, it allows you to do sort of domain-specific optimizations, where you can sort of optimize the code you're generating based on the early input you're seeing. So if you want to implement a matrix vector multiplication product, and your matrix remains often the same, but the vector changes quite a lot, you might want to actually inspect the shape of the matrix, which is your first input, and then generate sort of specialized code depending if the matrix is a diagonal matrix or it's a sparse matrix, so that eventually when you see the vector, the multiplication or the product is computed more efficiently. And in fact, one of the biggest machine learning libraries for this kind of thing in C++ is using exactly this form of metaprogramming. Now, it's also very useful to eliminate boilerplate code. Yeah?
So, in the previous slide, you had this eval operation.
Yeah.
Part of the challenge for typed languages is that reflectively the type of eval is not typable.
Depends. I'll get to that at the very end of my talk. Okay. Keep that thought. Okay. It's a very good thought, and we'll get there. So if you have a boilerplate code, when you want to eliminate that, that's also very useful if you have templates and macros, and that applies for both the programming and the proof setting. And in proof environments, you often use something called proof by reflection. So in MetaCoq, what you can do is you can quote a term in Coq, and you get it encoded. They have a data type implemented in Coq itself. So you get it into that kind of syntactic representation. You can use Coq itself to write programs about it, and eventually you can actually reflect it back. Now, there are also not so good things about it. One is that when you want to actually reason about code generation and the generated code, it's actually quite difficult. In particular, it's very difficult to preserve certain invariances that you have only scoped representations of code or well-typed representations of code. So from the languages I've put up here, in this line here, there's actually only one language that supports a form of typed metaprogramming, and that is MetaML. And that is sort of surprising because if you think of a system like Coq or Lean, these are dependently typed systems, but with the representation you actually get is basically raw syntax. It doesn't know that 2 + 2 is a piece of code of type NUT. It's just that it's a piece of code. So you can do compositions that says true plus true, if you like, and that would be fine because it's still a piece of syntax. It just will not run. Yeah.
Just one comment. So in New Code, there is a library called Code4, which tries to do some of these things by typing quotations. It's not, there's no Type-Theoretic issue with it, so it's not, but it does.
That's right.
Help with it.
Right. So this is getting to my third point, that there are some type-theoretic issues with it, so there are not only practical issues that some of these errors get caught only at runtime, but more fundamentally, there are type-theoretic issues, and both of you have pointed it out, especially how do we do run, how do we actually characterize typed representations of syntax, and how should we manipulate these things?
Great. So, just regarding the references, the Boyle theorem is really the source mode of reflective reasoning, and ACN2 is completely reflective system. Both of these are kind of pioneering in a way. Some of these others
probably I should add them in there. And I would say, so the practical effect is that errors are caught essentially not at generation time, but at runtime. But from a theoretical point of view, as some of you already said, what is that type theory that we're actually working with? Because if you look at these systems, they usually have, it's an engineering hook that is built into these systems that either allow you to get access to the internal representation of the syntax of the actual system, okay, or quote it into some kind of data type that exists in this proof environment. Okay, but it's engineering. Okay. So it's not that we have a calculus of construction plus quote, okay, or a Martin-Löw type theory plus quote. Okay. That is sort of still elusive. And that is really what I'm interested in. Okay? So what I'm interested in is really figuring out what is a good type-theoretic foundation for metaprogramming in the presence of dependent types. Okay? So full dependent types, universes, type-level computation, things like that. So we'll start at the beginning, okay? Because in order to understand what the challenges are, we first sort of need to understand how to represent code, okay? And some of you bear with me, okay? Probably it's like, oh, I've seen this before, but I think it's good to remind everyone what it means to represent code. So the simplest example is, let's say we want to implement or represent the code of this lambda calculus, okay? It's a mini, tiny language we're working with. You can certainly add in also natural numbers and other things, if expressions, whatever you like. But the essence is already there, okay, if you have a little lambda calculus. And we have types, nat and ARB, and we have variables, a way of creating functions, lamx, which has a type annotation A, and has a body M, and then we have application M applied to N. And there's this intrinsic notion of binding that X appears in M, and X binds this occurrence of M. And so, how would you teach this to an undergrad, how to represent this language, okay, in your undergrad class? Well, if you use something like OCaml or Haskell, then you might define a type obj for your types that has nat and arrow as constructors. Arrow takes in two objects. And then if you want to represent your terms, then you have maybe represent variables by strings, okay, because you don't know any better, and it's the easiest for students to understand. And then you have the representation of functions, okay, which takes in as a first argument the name of the variable, which is a string, then the annotation, which is an object, and the body, which is a TM. And applications are a TM across TM. And of course, the problem is that this representation here doesn't have any built-in notion of binding, okay? So I could have a variable y occurring in the body that is not meaningful at the outside. And if you wanted to represent these kinds of object terms, then you just literally translate them, right? The x here is going to be turned to an x, a string x, and it happens to be the string x that I'm referring here. But as soon as you get to something like overshadowing, where you have lamx and lamx applied to then returning x, right, which refers in fact to the second innermost x, then it's a bit less clear what the syntax tree actually means. Okay? And you would need to implement some notion of equivalence or alpha renaming if you choose that particular representation. And in the last case, we just really have two distinct variables, f and x. Okay? And it turns into this abstract syntax tree that we had before. Now, you might know how to do better. Okay, so there's in fact a whole zoo of representation techniques. You might use a numbering technique, okay, where you get rid of this idea that you need to alpha rename certain variable names because you have chosen a unique representation scheme of your variables. Okay, you might use something like locally nameless. Okay, you might use something like nominals. So there's a whole list of representations I could use. But there's sort of this trade-off, right? You have to think about what do you do with explicit with renaming and what do you do with substitution. And we know by now, right, if we implement these kinds of systems in proof assistance, that there can be quite a lot of overhead in dealing with doing renaming and substitution operations and lemmas about them. So, I would say I can give you immediately 3 different studies which say that 70% of the code they've written for a particular mechanization is spent on doing this kind of boilerplate code. So this might not be the best representation to use also for metaprogramming. Okay? It would really expose some kind of raw syntax, where we need to work with. But in some sense, we work with higher level languages, right? We have rich type systems. We should be somehow doing better. So, so the key, I think, to this is to find the right abstractions. And I particularly like this quote by Barbara Lischhoff. Okay, she says, the motivation behind the work in very high-level languages is to ease the programming task by providing the programmer with a language containing primitives or abstractions suitable to their problem area. The programmer is then able to spend their effort in the right place, and they concentrate on solving the problem, and the resulting program will be more reliable. Clearly, this is a worthwhile goal. So the goal is, in some sense, to have a more abstract representation of our syntax, and then build on that a meta-programming foundation. Okay, so it's always good to know where we're coming from in order to know where we're going. And I like the 80s. Okay, the 80s had great music, great hair, fashion comes back. The 80s are good. So, well, there are some other things that happened in the 80s. In particular, the logical framework was proposed as a way of representing syntax, in particular to define logics and languages. And what is LF? Well, LF is essentially a dependently typed lambda calculus, okay, where we represent formal systems in it. Okay, and so the LF itself, or the lambda calculus we use there, knows about functions. Okay, we implement them once and for all. They know what it means that functions are renamed. They know what it means to apply functions. Okay. And what we're going to do is we're going to leverage that function space to model binding in our current language. Okay. And that is what is called higher order abstract syntax. So let me show you. Okay. So we're back with this particular example. Okay. And the way you would implement this is by defining two types, okay, obj and tm. And now we have here two constants, nat and arrow, corresponding to the nat type and the function type. Okay. They're pretty much similarly implemented as before. They take in two objects, produce an object. We have app, okay, which takes in two terms and produces a term. But you notice that there's no variable case. And in particular, our function, this notion of binding we have here, okay, which is with this arrow, will model with a function space, okay, from tm to tm. How does this play out with a set of examples? Well, if you have the identity function, okay, it means you have the constructor, type of the annotation, and then the body is modeled as a Greek lambda, which is the LF lambda, x point x. Okay? So we get immediately alpha renaming, so lambda, if you would have written here a y, that doesn't matter, okay, because we know how to rename functions here. You get overshadowing, okay, so even if you have here an x and a second x, you can certainly write here x and x, but since we use a language that is rich enough, which is a lambda calculus, it knows already about alpha renaming, we get alpha renaming for free. And in particular, we get also substitution for free, because, of course, this language has these Greek lambda functions, and they have a notion of beta reduction. Okay. So this idea scales. Okay, so for example, if I want to now add in polymorphism, okay, I have here a universal polymorphic type for all alpha a, and I have polymorphic type variables, and I might add in a function space that abstracts over polymorphic variables. I might add in a let expression, okay, and I have always these orange arrows that tell you where something gets bound. Then we can now actually represent this, okay, just following the same idea. We have a binder here, so we will have object to object, it's a function, okay, because the type variable gets bound. We have here object to tm for our type abstraction on the term level. And we have here another function tm to tm to model the fact that the occurrence of x in n is bound by this let x. Okay. So whenever you have something that gets bound, it's mapped to the LF lambda. Okay. So if you look at the examples, okay, I have here a type variable alpha that is going to be bound and being used here. Well, I have a lambda a for the abstraction over the type variable, and I have a lambda x here, both these Greek LF lambdas that are abstracting over the term variables. Okay. And if I wanted to model my polymorphic function space, okay, I have here all, but I have here a lambda a lambda b. So the slogan is really, right, that you have an abstract syntax tree with a built-in notion of a binder, and Dale Miller sometimes calls these trees lambda trees, okay, because they have this internal built-in notion of a scope. And I can even make this intrinsically typed, okay, if I want to. So we saw some typing rules for the lambda calculus this morning, okay. So I now basically introduce TM with a type family. It's indexed by an object. And now I basically, whenever I use a TM, I actually say what's the type of this term, okay. So lam is actually characterizing a function of type A arrow B. Okay, so that means the body is of type TMB, given that I have a variable of type TMA. Here you see that I did a universal quantification over A, but think of it that also B is universally quantified, it's just implicit. Okay, I didn't write the universal quantification explicitly there, but it can be reconstructed. Okay, and yeah.
Is TM from type to object or object to type?
TM is from object to type because it takes in as an argument an object and creates a type.
Okay.
Yeah? Yeah?
So would, with this encoding, doesn't it seem like now TM of R is just sort of pointless and you could have used TMA or TMB? Like what, couldn't you just use the meta level at this point in order to represent all of your terms and functions?
I could, yeah. But then you can't index them because you can't index TM by TM itself. So, yeah, so I mean, this is also points to a sort of limitation of this intrinsic typing approach, right? That we don't know how to make this work for a fully dependently typed language, for example. Yeah. But for simply types, it certainly works. Okay, it works for polymorphic types as well. Okay. So we can push this quite far, but all right. So the lesson to take away from is that really these LF functions, okay, are encoding the variable scope. They are really, they don't have recursion, okay, they don't have pattern matching. It's a lambda calculus. And that is actually also important, that they are really characterizing just the scope of variables. Okay. But what you do get is that, in fact, a representation, right, the object I wrote on the left side of this table, there's a one-to-one correspondence between the object I wrote and its representation in LF. And if I have a representation in LF, that is in a canonical form, it corresponds exactly to one element in my object language. Okay? So there is a bijection between these. Okay? There's nothing like exotic terms, or there's not a predicate that says it's a well-formed term. Okay? There's nothing I implement here, this is a well-formed term, well-typed term. Okay? It's intrinsically informed by the foundation we're using. Okay. Yeah?
So one advantage of just the abstract syntax tree representation is the ability to induct dimension recursion.
Yeah, I'll get there. Give me maybe yeah. There's maybe you think it's cool. Okay. You think it's cool. I said, you know, I was given, you know, I'm speaking to a more general audience than like the 3 people here in this room. But you know, if you're coming from OCaml Act or Lean, you know, the first question might be, okay, that sounds cool. I want to do that. Okay, sounds like good. And then your next question is, how do I write recursive functions? I'm going to answer both of them. Okay. So, all right. So, I mean, I like OCaml, so I will do something in OCaml. You define a type TM. Okay. Just as we did before. Okay. I removed var and app because it's not that important. And I'm defining a constructor lam, and it takes in a function, tm to tm, okay? Sounds like this is exactly what I just told you, okay? And then we'll define apply, okay, as a function. It does pattern matching, okay, it takes as an input a TM. It's clever, it says, oh, TMs are defined by this constructor lam, so I'm going to look at this constructor, and I'm extracting f, okay, which is the function that is being defined. And then I'm defining a term omega, okay, which essentially says lam is a constructor, okay, function f is my OCaml function, okay, and then I say apply xx. So, I mean, I already picked very conspicuous names here, but what do you think will happen if I now run apply omega omega?
Loop.
It'll loop, okay, yes, it'll loop, okay,
Won't the type checker complain before it loops?
no, it will not, oh no, camel, it will not complain.
No.
It's OCaml.
Yeah.
It will not, okay, so this is what will happen is it will call this function apply, right? So it will look at the definition of omega, it will unpack this function, okay, which is defined to be apply xx, and then it applies this omega and plugs it in for these two axes, and you get again apply omega omega, and then it will continue. And the interesting thing about this very tiny example is that I just wrote a non-terminating program that will loop without having written a recursive program, okay? And this is indeed, it will loop, and this is the fundamental reason why you have in Coq or Lean, essentially you cannot write these definitions, as Jacques was pointing out, right? It violates what is called the positivity restriction. Okay? And if you would allow such definitions, your foundation would be not normalizing and therefore not being consistent. Okay? So you can't have that representation technique, okay, in Coq and Agda. Okay? This is the sad news. Okay? But I'll show you how you still can get it. Okay? So don't be too sad. Okay. So there was another question, right? But that was about. And the reason I should say, right? Why can you not have it again? Is because if you think about the status of functions in these systems, from Camel, Haskell to Coq or Lean or Agda, the functions are really opaque. There are black boxes. You can observe their behavior by passing them arguments, and then you see what they will compute, but you cannot inspect their syntactic structure. But that's, of course, what you exactly want to do when you have syntax trees, right? You want to actually inspect that syntactic structure we just defined, okay? And so that's exactly why Shankar said, I want to write recursive programs, okay? Okay, so how do we write recursive programs, okay? Here's an attempt, okay? Let's say I write a program. It's a bit of like a meta program, if you like. It takes in another program, okay, and wants to compute just the size of that program, so the size of the abstract syntax tree, so how many constructors are used, okay? So I start off, okay, by saying I want to compute the size of lam x, lam f applied to f applied to x, okay? And as I make my recursive call, the red x becomes free, okay? So I would need to do something with this x, so clearly there's something going on. And I count one, because I found one constructor. And I'll keep doing that recursively, but you see that now the f becomes free. And this is, of course, a problem. Okay? So in the 90s, there was a lot of work on how to fix this problem, and in fact, it prompted Andy Pitts and Jamie Gabai to write in one of their papers, the whole higher abstract syntax approach, by its very nature, just allows a feature that we regard of key practical importance, the ability to manipulate names of bound variables explicitly in computations and proofs. So that was a quite radical solution then. They said, well, let's get rid of higher abstract syntax and let's do nominal. But we don't have to be that radical. Okay? So in particular, if you go back not that long ago, 2008, we revisited in sort of what it means to characterize holes in higher abstract syntax trees. Okay, how to characterize subtrees in this larger tree. So if you look at this first example here, and this is what might be sitting in a hole. Okay, and how could I abstract over this hole? Okay, how could I give it a meta variable? So you were talking about meta variables the other day. And the same thing here, right? I make a recursive call on this subterm. Okay? And I'd like to make this in a meaningful way, this recursion. And so the idea is that we look at first at what is the typing for these LF objects, right? These are LF objects in our language. And if you know something about typing, it's usually a three-place relation. You have the term, M, okay, that has a type A, in some context, psi. Okay? And so if I now instantiate the context and the term, okay, this expression up here, is indeed a term, again, namely this thing. And now the X is bound. Basically, it refers to this X that is in my context. Okay, so the question then is, okay, still, what is this thing that is in the box, okay, that I just characterized, and what is this thing that maybe is this box? Well, the answer is we should always think of this within the context it lives in. Okay, so this box here is a TM that lives in a context where I have an X. Okay. And this sub-expression is a TM that lives in a context where I have X and F. Okay. So that is what we call a contextual type. Okay. It's in fact a modality that allows us, that we generalize to being a contextual modality. And that allows you to characterize these holes in these trees. So in 2008, we wrote a nice paper which is called Contextual Modal Type Theory, together with Alexander Danevsky and Frank Fenning. And the idea is that you want to reify essentially this typing derivation into a type. And if you think about this, this is what we do often in logic. Okay? If you have a hypothetical derivation that depends on assumptions, we internalize it by an implication. So we can talk about it at the propositional level. If you have a parametric derivation that says something for all students, right, and you did this generically for all students, you internalize that with a universal quantifier. So you can talk about it on the propositional level. And so here, we're internalizing essentially a typing derivation, or if you like, a beefed up implication, an implication that is actually applied to multiple things. And logically, it corresponds to a generalization of the modal logic S4. So it's actually logically grounded. So how does this work? Okay, well, if you want to now refer to this whole H, okay, that is here. Okay, I define the type of H up here. I said it's a term in a context where I have X and F. Okay, so that's my meta variable context. And I then can plug into here this term at fx to get my original term back. Okay. So, okay. Now, I'm already waiting for some objections here, because you might say, well, really, you picked very cleverly here these names, that they line up to the names you have here. Okay? And, I made this whole speech that we should be modulo alpha renaming and stable under substitutions. And so, we should really not depend on the fact that we chose the same names here, okay? Because they're different scope, if you like. Okay? And the answer here is, well, okay, we should maybe be a bit more careful. And so we want to be stable under alpha renaming, okay? And we want to define carefully what it means for doing a substitution for these whole variables. And the answer is that we associate H, which is the whole variable, with a substitution. So if my whole here uses the names Y and G, and I want to paste it into a context where I have X and F, I apply this renaming. Okay. So the usage of a contextual variable always comes with a substitution. Okay, it's a closure. And so that means if you want to define typing models for this system, then you have two different variables. Okay? Your normal local variable, okay, which is the LF variable that refers to variables declared in psi. And if you have a meta variable that comes from gamma, it will come with its own local context. Okay? And then you need to port it from y to my current context. I need to bring it into my local scope. And so here sigma here is a general substitution. It doesn't have to be only a renaming. It can be actually something that does a proper substitution as well. Yeah.
Previously when you had like variables that were renamed, you used function types in order to do this. So why higher order abstract syntax sort of using this LF function type? How come you aren't using LF function types to replace this closure notion? Why couldn't this just be a function?
Yeah, that's a good question. Okay. So if you use functions, okay, here you would write, you basically give H a function type, okay, which is type tm to tm to tm, okay, because we have these two arguments. Actually, it should be a function tm to tm, okay. Then when you plug in something for H, you create an administrative beta regex that needs to be then computed. So the original motivation, in fact, of this contextual type theory was to define a system where you don't create these administrative redices. Okay. And that means you can actually talk about unification in a much cleaner way, for example. Okay. And I mean, I should also say that ideas to this, in some sense, existed prior to this. Okay. So if you look at the work by Gilles Douek, for example, he has an explicit substitution calculus for unification. He also has this notion, and he calls it pre-cooking. Okay. It doesn't have a logical status. Okay, so part of the contribution of this work was to first unify some of these different ideas where people wanted to talk about wholes, and also give a logical status to some of the issues that then arise when people were talking about meta variables and characterizing them as functions. Yeah. So when we go back to this notion of this program size, we now know how to write it. We write it not as a program that transforms terms, we write it as a program that transforms terms that live in a particular context. And in the beginning, the context is empty, and then as we do recursion, we populate it. Okay? And so everything remains locally scoped. And so the size of this the function size now has type for all contexts, gamma. If tm lives in this context, gamma, I can return an integer. And it's written by pattern matching on these contextual objects, tm's that live in the context gamma. So of course now it's not like your normal pattern matching like in OCaml, okay, because tm contains functions, okay. So we have higher order terms here, but we know how to do higher order pattern matching because, for example, we have the algorithm by Dale Miller back in the 90s. And this can be done also for, I mean, I hear about only TM, but you can also do this for well-typed terms, okay? Then you have an additional argument where you say for all gamma, for all A, if you have a term in A and gamma, then you return an integer, okay? So this scales, and this is indeed basically how Beluga is implemented, okay? Beluga is a programming language that can transform these contextual higher abstract syntax trees. And if you like, you can think of it as a meta-programming language for code. Okay? And Beluga is a two-layered type theory, if you like. Okay? It has LF at the bottom, and at the top, it has a system that is sort of equivalent to sort of a first-order logic with a particular domain, namely the domain LF. Okay? And in LF, you can then implement different systems. Or if you're coming from type theory, it's like an indexed type theory. And it can generate code, it can compose code, it can recursively analyze code, and suspiciously, okay, because Shankar asked evaluation, there's no evaluation. So, all right, so this is good. I want to show you a little bit what other things now we can do in metaprogramming you might want to do. So typically, I cannot give a talk without the power function. So every talk about metaprogramming has to have a power function. So here it is. Again, we want to build a term tmnat that depends on x, that is a tmnat. So this code here raises x to the power of this input. So if your power is 0, of 0 is going to be returning 1 in the context where you have x and x isn't used. Okay, and if you have power of n, then you call power of n minus 1, okay, and you splice it here in, okay, and here we'll see why functions are not so great, okay, because we can simply splice it in and we'll get essentially our final result, okay, so if this power of n minus 1 was computing 1, it'll be computing 1 times x, okay, and if if this was power of 1, it's computed 1 times x, we'll now splice it in, and we multiply it by x. And this is made to work because really, when we splice, there is an actual renaming, okay? And that renaming is applied as soon as we know what the recursive call computed. If you have functions, it will create an administrative regex, and it will not, you will not have this representation of the code. So especially if you care about pattern matching and analyzing code, this, I would argue, is much preferred. But you can do even better, okay? So let's say here you have two constructors, head and tail, which extract the head of a list and the tail of a list. And you could make this polymorphic if you like, okay, I didn't. And you want to extract the nth element. So if n is greater or equals to 0, okay, 0 will start counting by 0. We'll extract the top element of that list. And now if we want to extract further down the road, okay, let's say I want to extract nth of 1. What do I need to do? Well, I need to take the head of the tail. Okay, I need to get first the tail of v, and then I take the head of that. So this head of 0 will come, and the nth of 0 will compute head of v. Okay, but I want to get the first element, not the 0th, so I'm going to plug in for v the tail of this v. Okay. So in the end, I get, when I want to have nth of 2, I get head of tail of x, okay, which is indeed what I wanted. So here we see that we actually do more than renaming, and it's quite elegant if we can do more than renaming. Okay, so how does this actually relate to some foundations we know that exist in metaprogramming? Okay, so there was some very nice work by Rowan Davis and Frank Penning around 2000, where they decided they observed that in fact the modal lambda calculus, the necessity modality, is a great way of characterizing this distinction between code that is necessarily true and can run at every stage, okay, and the program that does the generation. And so they describe this as a simply typed system, okay, and if you restrict it to 2 layers, okay, because they had also a multi-layer system, multi-stage system, what happens is essentially you represent the code as a simply typed lambda term, and at the outside, okay, you have simply typed lambda programs, possibly with natural numbers, okay, but you also have a quote, which is a box, which allows you to access what is inside here, okay, and they had an unquote, which allows you to do splice. And so this was at the same time as Valeria and Gavin were working on the modal lambda calculus, for example, right? So it is really, a well-studied foundation, if you like. But it was, of course, only simply typed, okay, and it didn't have recursion. Okay? So it doesn't do recursion. I mean, it doesn't have recursion on code, I should say. So this is a little cheating, but I give you a high-level view of what Beluga does. Okay. So in Beluga, we have a separate system of how we represent code, okay, which is LF. So we encode simply typed lambda calculus in LF. We can encode system F in LF. Okay. We can encode whatever equational theory you're working with in LF. Okay. And then we have this outer layer that is essentially I called it STLC star. It's more like an indexed type system with contextual quote, contextual unquote, and recursion. So you can access hierarchical syntax trees, you can compose them, and you can analyze them recursively. Okay? And again, we don't have eval. And so more recently, okay, in 2019, we actually extended that outer layer to what is called the Martin-Löw type theory. So the type theory that, for example, underlies Zacta. So it has a full universe hierarchy, okay, and it has also a contextual quote and a contextual unquote, and it has recursion on code. And when you do a quote, you access things encoded in LF. Okay, when you do an unquote, you splice in things that are LF representations. Okay? So you go still between these two worlds. And that means that it gives you the power to define your own sublanguages, right, of Martin-Löf type theory. I can implement STLC, I can implement something more powerful, I could do explicit typing derivation if I want to, because I need to implement Martin-Löf type theory itself in LF, okay. So I can choose what I implement. And the interesting thing is, since we have actually the power of doing recursion and we have Martin-Löf type theory, now I can actually implement an eval function that takes in, let's say here, your STLC term and reflects it back into Martin-Löf type theory. Okay. So I don't need to add eval first class anymore into the system, as Rowan and Frank basically had this for free in the system by design. Okay. Now in this system here, you don't, okay, because you actually have the power of recursion on these syntactic objects, and you can write essentially a customized reflection engine that reflects STLC back into Martin-Löf. Now you can't do this for every language, because System F would not be a sublanguage of Martin-Löf, but for those that are, you can run. Okay. So Cocan, although we didn't pitch it back then in 2019 as a meta-programming system, we pitched it back then as a system where you can get the benefits of encoding logics in a system like ACTA or COC. It is actually a meta-programming foundation. So, how did we prove that this is actually consistent? Well, we proved this by essentially a Kripke logical relation argument, okay, where we prove normalization. And of course, it's not trivial, okay, because you have type-level computation. So, a simple argument of erasure doesn't work. And we use a technique by Andreas and Gabriel Scherer, where we define the logical relations for well-type term based on the recursive semantic type. And the key part is to break the cycle, right? You have the cycle between quote and unquote, and you might think, oh, I'm going to go around this cycle, and if I have a cycle, this is bad. Okay. And this is true, but you can break the cycle because you will stop as soon as you have reached something that is a neutral term. And once it's neutral, then you just fall back to equality. Okay. So, since then, what has happened? So first of all, for those of you who are interested in category theoretic foundations, so with Ulrich Schöp and Jason Hu, we actually developed a category theoretic foundation for the system. And it turns out that it is really a syntactic type theory, with an algorithmic equality definition and everything, for Martin Hoffmann's semantic analysis of hierarchical syntax. So it is, you give it a pre-sheaf model and things kind of work out very nicely. So in the last 5, 6, 7 minutes, I want to talk about some of the very recent work we're doing. Okay, so this, one question is, how do you implement a system like Cocan? Okay? And you could certainly say, and this is how traditionally proof assistants are implemented, I have a theory, I'm going to now choose my favorite language, could be C, could be OCaml, could be Lisp, I don't know, okay, and then I'm just going to write up, my definitions and have a type checker. But then the question is, how do you know that this implementation is actually correct, okay? And so we're going to do a different approach to this, okay? Basically, we're building a proof assistant from the ground up. Okay, so we're in the process of basically implementing Cocan in COC or ROC. So, and we're going to use not this reducibility argument, but using an argument called normalization by evaluation. Okay, and that builds on some experience we have of implementing normalization by evaluation algorithms and proving them correct in ACTA for modal type theories. But the reason we're using COC is because COC has a lot better extraction mechanism. And the reason we're using NBE rather than the traditional logical relations argument is because it's much more compact. Okay? So our implementation of full Martin-Löf modal type theory in ACTA is 11,000 lines of code, okay? Including all the proofs. Okay? So, so that is the reason we think it's much more manageable. Okay? So compared to Kenji Mayar has an implementation of Martin-Löf type theory with this style of proof we used for Cocan, and it's already over 33,000 lines of code. Okay, so, and there's no possible extraction from it. So what we've done is we so far mechanized this NB algorithm just for Martin-Löf, okay? And we have implemented a functional NB algorithm and its declarative version. We proved that they are correct. It has a full universe hierarchy, it has subtyping, okay? And we actually are able to extract an NB algorithm out of this. And what we wanted, we have the NB algorithm for Cocon on paper, okay? So now we'll need to implement the extension for that and that. And so that is some joint work with Jason Hu and Junyang Zhang and Antoine Gaulin in my group. And that means it's a trusted backend, okay, for a proof assistant. And so then you can build untrusted front ends, and you can build up more trusted layers, but from the bottom. Okay. And there are a couple of other projects I want to mention, okay. So the first one is, I already mentioned in passing, that is a cryptocide full modal intuitionistic type theory, okay, called MINT, that we did design, and there's no pattern matching, okay, and in fact code is treated as a black box, okay, so it's assumed that some kind of compiler would do the optimization. You still get separation of early inputs and later inputs, okay. But it was sort of a study of lifting what Frank and Rowan had for the simply typed system to a proper type theory. Okay. And we decided when you lift things to a type theory, the question is always what kind of equational theory you have. And we decided to have an equational theory inside and outside the box. Okay. We now know better. Okay. In particular, is this last work here, where we have really taken to heart this two-layer system that we have in Cocon already. Right? We distinguish the language that represents code and the language that writes programs about the code. And that gives you a layered type theory. And with Jason, we have a paper at ESOP that describes that type theory for simple types. And very recently, we've extended that type theory to a full dependent type theory, where you have the code is MLTT syntax, okay, pure syntax. The type of that code is your MLTT as you know it, so with an equational theory, okay. And the layer where you write programs is essentially MLTT plus quote, okay, and recursion. And then Möbius was some work at Papel in 2022 where we did code generation for system F-style systems. Okay. They didn't have a normalization proof, but it is extending what people have been knowing how to do for metaprogramming in programming languages. And then there are two more directions I want to mention. So one is substructural logics, what Sandra talked about. Okay. So you might want to wonder, how can I do metaprogramming and give also resource guarantees? Okay, so that, for example, the code I'm generating is garbage free, okay, or that I have certain information flow properties about the code that I'm generating. And so recently we started a collaboration with Frank Fenning and Sophia Rocha on designing what is called using adjoint modalities. So adjoint modalities are sort of split this box modality into two parts, and they give you sort of access to the pointer where code resides and the representation of the code. Okay. And since this is really a unifying system, you can actually give, I mean, this is one step in that direction. This is a Nash reduction calculus, but with Claire, my student, we've been using it as a foundation for metaprogramming that provides resource guarantees. And the last point I want to make, if you think about layers, okay, another question is, you might have, you want to build metaprograms about languages that have nothing to do with what your metaprogramming language is like, okay? So you want to write metaprograms, let's say, about Rust, okay? And you might not want to use Rust to do this metaprogramming because you're implementing a compiler, okay? So as a case study, let's say, right, of doing metaprogramming over a completely different language, we have looked at generating and analyzing session-type processes. So session-type processes is essentially logically a sequent calculus. Okay? And the outer layer is a functional language, which is a natural reduction calculus. And here the contextual modality mediates between Nash reduction proofs and sequent calculus proofs. And if you think of it as a Curry-Howard interpretation, what it does, it mediates between a functional language and a language that has an intrinsic notion of concurrency or shared memory. And that opens up a lot of new things of what you want to think about. So what I wanted you to take away is that layers are good. Okay, one should distinguish between syntax, okay, which represents code, and control what kind of equivalences we want, okay, on syntax, and we should then consider sort of programs that manipulate syntax. And we can make this precise logically using these contextual modalities. So layering allows us to grow metaprogramming systems in different dimensions. Okay, we can grow it to a dependently typed system, we can grow it to a system that transforms session type processes, if you like, we can incorporate resources. Okay. So it's really enabled by this fact that we have this distinction between code and programs, and we can have multiple layers in there if we want. Now, I think if you don't take anything else away, the most important lesson for me is actually 3. Okay, my favorite number is 3, that's why it's 3. Contextual higher-order abstract syntax objects, okay, provide a high-level representation of code that can be used for pattern matching, where you don't have to manipulate the Bruin indices and you get a notion of intrinsic scoping and intrinsically well-typedness. And so if you're thinking about doing metaprogramming, we should have OAuth, I think, in the system. And pattern matching on code in your outer layer, okay, really enables you to do evaluation. Okay, so that means you don't need to build in evaluation, but if you have the power of recursion on code, then you can implement customized evaluators, essentially, or reflection. All right, that's it. So thanks for coming.